Let's see. Next up, we have Lukas, who is going to be talking about Apple's in-house. Well, I'll let him tell us what he's talking about. But super cool. We're kind of switching over to iOS. So round of applause for Lukas.
Okay, awesome. Welcome. I'm Lukas, and I'm currently doing my master's thesis at the Technical University of Darmstadt. And today I want to get to the bottom of Apple's novel C1 baseband. But before we dive into the C1 itself, I just want to give you a short overview of the various basebands used in Apple products, such as Apple Watches, iPads, and iPhones. And currently, the relevant manufacturers are Qualcomm, Apple themselves, and also MediaTek, which has been newly introduced with the latest generation of Apple Watches. And each manufacturer also has their own Apple internal code name. And yeah, it's also interesting to note that Apple just bought the modem division from Intel in 2019, which itself bought it from Infineon in 2010. And the newest basebands support satellite and features and also 5G. But we want to focus on iPhones in this talk, so they basically did the whole evolution of the baseband stack, and the latest iPhones ship with Qualcomm basebands and also Apple's custom ones. We can also look at it from another perspective, because in the context of basebands and iPhones, it's pretty interesting to analyze how the iOS operating system and the baseband communicate. And this is called the iOS baseband protocol. And for Qualcomm basebands, there's the Qualcomm MSN interface. This protocol is also being used in Android smartphones and so on. There are some open source implementations available, but Apple does a lot of custom method extensions, protocol extensions, and so on, which we analyzed and presented last year at OBTS, so I'm glad to be back. And also for Apple basebands and also the Intel basebands, there's the Apple Remote Invocation Protocol. And this has only been seen in Apple products so far, and it's a new protocol which has been reverse engineered by Tobias, like a student some years ago. And it enables us to automatically basically recover structural information from iOS system libraries. And this is also open source. And if you look at the right side, you can see this kind of timeline. And with the reappearance, basically, of the Apple protocol, it happens with the introduction of the C1 baseband in the iPhone 16e. And now in the iPhone 17, we got dual solution because Qualcomm basebands can deliver some more features, which we'll dive into later on. And yeah, we could just use our old tooling to basically analyze the new Apple basebands, or at least their communication structures. And we found there are new structures for 5G and satellite communication as expected, because those features weren't present on Intel basebands. And we could also simply update our application to make use of those new structures, so you can analyze basically your cellular data on the go for the C1 basebands. And C1 is actually pretty relevant for current and future research, because it is expected that Apple will switch at some point to only their internal basebands, because the contract with Qualcomm is set to run out next year. And the first iPhone which shipped with the C1 was the iPhone 16e. It was unveiled in February, and the iPhone Air, unveiled in September, introduced the more efficient C1X baseband. Maybe it has like a more efficient silicon, or is using a better build process, because the firmware for both basebands is exactly the same. Yeah, and the iPhone 17 and iPhone 17 Pro still use Qualcomm basebands to support millimeter wave. And yes, that's almost about it. And we can begin looking at the actual hardware architecture of the C1 basebands. iFixit did some teardowns, and there you can basically identify the baseband chips. They have the part number APL1114, and their own SoC, and they are positioned at different angles on the logic board. And based on some sources, we can also reconstruct the abstract schematics of the C1 chip in the iPhone 16e. And we think the chip itself hosts at least one ARMv7 core and also 4 ARMv8 cores. It connects to the baseband's power management unit, which is a whole set of chips itself, and ensures that the baseband uses as little power as possible. It also connects to the radio chain, so this is the actual part that sends signals over the air, and in this case it's a frequency range 1 radio chain, so it supports like the traditional sub-6 gigahertz frequencies, and also connects to chips for the global navigation satellite system, so like GPS and stuff. And in terms of storage, it connects to the system's SRAM, DRAM, and also a custom EEPROM. And also you want to be able to like connect to a network, so you have to plug in your SIM card or install an eSIM profile. And depending on the iPhone model, there are also connections to those components. And users also want to be able to actually like use their baseband and send data and so on. So there's a connection to the application processor. And also Wi-Fi and NFC work in similar frequency ranges. So they must communicate with the baseband to not interfere with each other. And finally, there are also some debug functionalities you can see below, but unfortunately they are not active on production boards. So it's not that easy to make use of them. And if we just like take a sysdiagnose on an iPhone 16e, we can already see like a lot of I/O connections within it, and also find there's a shared disk. We assume that's being used to transfer crash logs from the baseband to iOS, which then can include it in sysdiagnosis. There are also components for interrupts, power management. As just mentioned, there are also some components for inter-device communication to enable coexistence, and also maybe something to detect if your hand is nearby the phone, because this also causes interference. And then there's like a PCIe device, which enables like an I/O service interface. And to this interface, there are various processes in iOS which connect, like NFC, COM center, and so on. And there's like some special stuff to enable real-time kit inter-process communication. There are some interfaces like ARI, I just presented that, and also some other ones which are not in use by any process. And I think like mmap debug will only be used for testing purposes. With that basic knowledge, we can dive into the firmware architecture of the baseband. And if we just grab an IPSW for an iPhone 16e, we can already see in its build manifest certain cellular components. This is basically all the ARM binaries as part of the baseband. And if we now extract the file, just a quick heads up before, there are many code names for the baseband. So it's named C4000, Sinope, Leda, and Intium 1. You might have seen some on the previous slides. But if we just like grab an IPSW, extract the firmware at this given path, then we find it's encoded with an Apple custom FTAB file format, which also has been seen on other embedded Apple devices so far. And some files or segments are again compressed, but IPSW takes care of this, so we don't have to worry about this. And now we got like a whole bunch of files, which we kind of can categorize. And there are, as we've seen before, like 4 ARMv8 cores, 1 ARMv7, and also 1 ARCv2 core, more on this later. The boot process begins with iBoot, but in a special wireless variant. Then the operating system starts. It's basically the ARCOS file, and it also includes some parts of the cellular protocol stack. Then we got various files, or 2 files basically, supporting the up and downlink data transfer, because that should work independent of other stuff and be fast. Then L1CS implements the lower levels of the cellular protocol stack and also some signal processing. And there are some more files which support the basically GNS implementation or GPS, how you want to call it. And this runs on an ARCv2 core. This is like a pretty old architecture. And our assumption is maybe Intel or Apple bought this core and IP in the past, and they just continue to use it because it works. Then we got a PCIe host controller, and it also does some power management, but this is only an ARMv7 core, and we assume this runs all the time, so it should be a bit more power efficient, and your input data is basically trusted, so you don't need that much security mitigations. And there are also some power management firmware and maybe memory management unit. They might be also connected to the host controller or the operating system. And if you just look at the file sizes, you can see like a lot of the functionality could be implemented in the RCross and L1CS files. And if we now want to load such a file into our reversing tool, we have to take care of a special firmware segment header at the end of the file. It defines how to load basically the code segments and data segments. And there are already some existing IDA loaders for this. And it's important to make sure that the file size is not, it could be also smaller than the actual size loaded into memory. We're using 32-bit virtual address spaces even for ARM64 binaries. So the kernel is then in a continuous memory space with the other stuff, and we have references across functions. We also should set like executable permissions. And the C1 can also dynamically load code segments of other cores and map them into, basically our core. And we will also see this later. And segment names can also appear multiple times because it's only 8 bytes here. And it's pretty useful to basically expand them with more data from the binary. And we will also publish our loader shortly after this talk for Binary Ninja, and this is like one supported feature. And now we got a whole bunch of segments, like some kernel segments, executable segments, and so on. And the first thing I want to mention is segments related to the operating system. This uses a new Apple framework, OSC kit, and basically all the text, data, segments, and OS segments in the RCross file are related to this. And then there are also quite a number of segments with already like known appropriations for cellular stuff. And one interesting thing to note here, for example, is we got a segment for the frequency range 2. This is basically a 5G term and refers to millimeter wave. So maybe Apple is already internally testing millimeter wave support for the next basebands, but it's not yet shipped on the current ones. Regarding memory, as we've seen a few slides ago, there are DRAM, SRAM, and also non-volatile memory. This basically refers to the EEPROM storage. And there's also a lot of cross-core communication for interrupts, shared memory, and also message boxes. And if we just like take a look, those colored segments can be loaded by the RCross file at some point. And yes, since the first release of the C1 baseband firmware in February, its code base has changed a lot. And if we now compare it to the baseband firmware in iOS 26.0.1, it's now in version 2 and also supports the chip revision B0. We assume there are like different chip revisions with different hardware kind of in all iPhones, but there's only one firmware which basically supports them all, and the version B0 could refer to the new C1X baseband. And there was like a high amount of binary changes across the version, so diffing is not that easy, but the file sizes is always increasing, so more features are being added, and the overarching concepts but remain usually the same. Some segments change, like the operating system segments have been split up in some kind of way, and there are new segments, for example, for 3G, so maybe Apple wanted to separate this old stack a bit more from the newer stacks. And with that basic knowledge, we can basically dive into the firmware and its mitigations regarding security. The boot process, as mentioned earlier, begins with iBoot. That's like Apple's bootloader, and it has a low-level bootloader component, basically, that extracts the files as we did manually before. It then checks the hashes if all the files are valid, and also assembles some kind of GNSS configuration based on some parameters. We assume it could be either time, location, or other parameters. Then we go to the CL4 kernel, which resides in the text and data segments of the RCORS file. And CL4 is Apple's custom implementation of an L4-based microkernel. Basically, those kernels usually support capability-based system calls. It executes in level 1, logs the upper range of the virtual memory addresses for its use. And so the code resides basically in 0FFFF and so on. But for reversing, we kind of strip this prefix. And it also supports logging up to 2 text regions to be read-only. And this is based on some parameters you presented during the boot process. And CL4 also has been seen on Apple exclaves. There has been a nice post or series of posts about it by Augustine. Then the kernel hands off to the root task. It runs in user space, but both the kernel and the root task seem to originate from a similar code base, and they also have to be compiled with similar parameters, for example, a similar page size. And the root task is also part of this OSC kit I mentioned earlier. It could translate to operating system core or compartment kit. The real name is not really known. And it processes, the root task processes boot arguments, handles some pointers, and prepares the global memory by typing it for later use. Then it also basically sets up PAC and ASLR, and the root task then maps 3 memory segments, or not memory segments, but all of the segments I presented earlier from OSC kit into memory, and then uses those to initialize 3 processes, and they relate to so-called compartments. Then it also prepares some interrupt requests, maps them to those processes, and then launches them. And those processes are defined in the app configuration. And there's the platform compartment with the PIT 1. It kind of has broad hardware access and also provides the basic OS functions like threads, queues, and so on. Then we got the over-the-air compartment with the PIT 2. It basically receives and also answers packets. It receives over the cellular network, so basically untrusted data. It has only very limited hardware access, and for some to access the speakers and the microphone, so we assume that's why there's a middleware compartment that only has limited hardware access but still processes untrusted data. And those compartments, they communicate via well-defined remote procedure call interfaces that are basically defined in the app configuration, so which calls across boundaries are allowed. And each compartment also has a set of startup tasks which are initialized in the beginning, and then more like long-running tasks which are typical for basebands are set up via the boot and mode manager. And some functions, if you call them from a certain compartment, they behave differently. So if you want to access the NVM storage using the over-the-air compartment, you basically get a panic. And luckily, Apple included some pretty common ARM64 mitigations on the C1 baseband. They are pretty standard on desktop operating systems, but not exactly for basebands. And they applied them to all ARM64 cores. The other ARM64 cores just boot using in a simple real-time kit manner compared to R cores we've just seen. And Apple ensures point integrity by using their custom PAC implementation, which has been also seen like on the M1 chips and Mac. And there's a great paper about it. There's like on my slides a link to it. And just as a fun fact, if we go through the pointers in RCOS, only roughly 10K out of 29K pointers have some diversity information. ASLR is also active, and each core basically gets its own offset or so-called slide. And to enable cross-core communication, it also receives all the slides of the other cores upon boot. This is done via patch base. So those are like little type length value structures in the beginning of some sections, which are populated with data upon booting. And so far, we haven't seen anything related to memory tagging extensions yet, but maybe that's an interesting feature for the future. And throughout the firmware, there are many assertion statements scattered. They basically check if the baseband is in the expected state, and if not, they just cause a panic and abort, because it's better just to crash and restart than to enter an inconsistent or even harmful state. And users just might experience a short disruption of service, but this only is critical in emergencies. And the firmware, when crashing, enters a spin lock. iOS's watchdog will detect this kind of spin lock and then restart the baseband. And there are also many intermediate assertion functions used by various subsystems, so quite a number of them. And yeah, you can also see stack guards. They are basically just a special kind of assertion failure. And now, those assertion statements also contain some pretty interesting reversing information because they have some file names, file paths, messages, and so on. And we can just grab all of the file paths and reconstruct the structure of the source code. I just did it only for 2 levels, but you can already see the separations for some stacks. And yeah, how is the security model holding up so far? So far, there has been only one publicly known CVE for the C1 baseband. It had a criticality of 8.0 and was discovered by 3 researchers from the Beijing University of Post and Telecommunications and fixed in iOS 18.5. And at Hexacon, Apple also announced changes to their security program because they increased the bug bounties of various, I would say, components drastically. And this also includes the C1 and C1X baseband. So if you now find a wireless proximity exploit, you can get up to $1 million. And an interesting fact is also that they said they never observed a real-world zero-click attack, only via wireless proximity. So they seem to be pretty confident in their security architecture and solution, yes, compared maybe to some competitors. But unfortunately, there are some limitations if you want to hack around with the C1 baseband, because when interacting with the physical iPhone 16e or Air, for example, you can extract baseband data, crash logs, and so on from system diagnosis, but sometimes there are just none because the baseband didn't crash. You can also extract baseband data from the system log or also send just over-the-air packets to your phone, like over-the-air fuzzing, but this is very time-consuming and you basically get no insight into the baseband what's happening. And there are also no jailbreaks available for the iPhone 16e and Airs, and also expect none in the future. So far, there's also no SRD with C1. I cross my fingers for next year, maybe we'll get one. And the best approach for dynamic analysis is basically to emulate the baseband firmware on your Mac or do native rehosting, and then you got a lot more insight into what's happening, but this requires a lot of work. So I'm not doing it alone. I'm working together with Lukas, Niels, Dion, Jiska, and Marius, basically on making this possible and then fuzzing the baseband. And we plan to continue our research, and I hope I can share more in the future. Thank you for listening. Okay, thank you. You can also just come to me after the talk and ask any questions. We will publish this loader also in our open source projects, and you can also just send me an email. So thank you.